See, continuation of resonance effect or mesomeric effect. So we completed resonating structures or canonical structures. What are resonating structures or canonical structures? The various electronic arrangements are called as resonating structures or canonical structures. Next, see resonance hybrid. What is resonance hybrid? It is the representative structure of resonating structures. Once look at this. This is one resonating structure, this is one resonating structure. Which resonating structure we use? If we use this structure, this will fill. I already told you now. If we use this, this will fill. That's why instead of using any one of these, we use a new structure that represents these two structures, that is called as resonance hybrid. Okay, the representative structure of resonating structures is called as resonance hybrid. Once look at this definition, the representative structure of resonating structures is called as resonance hybrid. Okay, look at this. These two are resonating structures and this is representative of these two. Means this will represent this and this. Okay, and this is called as resonance hybrid. Okay, right. Let us see the characteristic properties of resonating structures. Resonating structures are hypothetical structures, that are imaginary structures only, hypothetical, imaginary. Okay, these do not exist in dynamic equilibrium because they are hypothetical. Resonating structures do not exist in dynamic equilibrium. It is not possible to isolate resonating structures physically, means by using physical methods or by using chemical methods. Okay, right. Next topic, conditions to draw resonating structures. These are very important. Okay, in JEE means several times questions came, right? In NEET also chance is there to get the question. So let us see the conditions to draw resonating structures. See the first condition. The resonating structures should differ in the arrangement of electrons only, but not in the arrangement of atoms. Let us see one example. Let us consider this as structure 1 and this as structure 2. Okay, I am giving labeling for this hydrogen H star, same H star. Okay, in first structure, this hydrogen atom means labeled hydrogen is present at which? Carbon, attached to carbon. Position of this hydrogen is at a carbon. In the second structure, that same hydrogen is present at which? Oxygen. Means here difference in the arrangement of atoms is present, right? Arrangement of atoms is different. So these two are not resonating structures. Clear? What is the rule or condition? Resonating structure should differ in the arrangement of electrons only, but not in the atoms. Here atom position is different. Here hydrogen atom is present on carbon. In the second structure, that same hydrogen is present on oxygen. So position of atom is different now. So these two are not resonating structures. Atom's position should be as it is. Here what is the position of hydrogen atom? Here also same only. If not, then that are not resonating structures. Clear? Right. I remember this point. Next. Rule 2 or condition 2. Resonating structure with more number of covalent bonds. Resonating structure with more number of more number of covalent bonds is more stable. Resonating structure with more number of covalent bonds, resonating structure with more number of covalent bonds is more stable. See this, I'll explain the reason also. What is the reason for that? Okay. This is one resonating structure. Okay. This is another resonating structure. Which is more stable resonating structure? See, first count covalent bonds. Second one, here how many covalent bonds are present? I expanded the structures. 1, 2, 3. 3 covalent bonds are present, right? Here 1, 2, 3, 4. 4 covalent bonds are present. See this point, resonating structure with more number of covalent bonds is more stable. Covalent bond means count single, double, all the bonds, right? Clear? 2 hydrogens, 2, 3, 4. 2 hydrogens, 2, and middle one 3. 3 covalent bonds are there. Here 4 covalent bonds are there. So resonating structure with more number of covalent bonds is more stable. So this is more stable resonating structure. This is frequently asking question. Which of the following resonating structure is more stable? Just count covalent bonds, very easy. Count all the bonds. Resonating structure with more number of covalent bonds is more stable. Very simple thing. Irrespective of positive charge on the more electronegative atom. Generally students will think that fluorine is more electronegative atom and it is having positive charge, it may be unstable. Don't think like that. Generally if positive charge is present on more electronegative, that should be unstable, but here we cannot go with that point. Clear? Irrespective of the positive charge on more electronegative atom, the resonating structure with more number of covalent bonds is more stable. Ignore positive charge on more electronegative fluorine. Ignore that point. Just see whether it is having more number of covalent bonds or not. Now coming to the reason, theoretical questions will come. Why this is more stable even though it is having positive charge on the fluorine atom? Let us see. Okay. Check the reason. Let us see the reason. I am drawing the structures again. See, one more point I wanted to tell you. Halogens are having how many electron pairs on them? Fluorine, chlorine, bromine. 3. Remember, halogens always contain how many lone pairs? 3 lone pairs. Oxygen contains how many lone pairs? 2 lone pairs. Nitrogen contains how many lone pair? 1 lone pair. Clear? Right. In the second structure, fluorine is having positive charge, na? I given fluorine is having positive. When fluorine is having positive charge, it is having only 2 lone pairs. Fluorine without positive charge, 3 lone pairs. Fluorine or chlorine or any halogen without positive charge, 3 lone pairs. With positive charge, 2 lone pairs. Remember that point. Okay, without positive charge, 3 lone pairs. With positive charge, 2 lone pairs. Clear? Right. Now we are going to reason. Going for the reason. Why this is more stable? Clear? Very, very important. Once look at this, all of you. This circle, pink circle. Pink circle. Observe pink circle. 1, 2, 3, 4, 5, 6. In the pink circle, how many electrons are present? Means around this carbon, how many electrons are present? How many valence electrons are present? Or electrons? 6 electrons are present. Octet is present? No, octet is not present. Now let us take another color, different color. Let us take white color. In this white color, white circle, how many electrons are present? 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons are present. 8 electrons are present. Means octet is present around fluorine, but here octet is not present around carbon. Remember that part, right? Okay. Coming to the structure, second one. Okay. In the first circle, around carbon, how many electrons are present? Count all the electrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay. In the second circle. One, 2, 3, 4, 5, 6, 7, 8. Right. Here 8 electrons are present. Here also 8 electrons are present. So that is the reason. Around carbon and fluorine, octet is present. That's why it is more stable. Okay. If you get the reason why, if number of covalent bonds are more, then why the resonating structure is more stable? Due to this reason only. Clear? Instead of that, you remember that simple statement. What is that simple statement? Resonating structure with more number of covalent bonds is more stable. Remember that. Over. Clear? Right. Next rule. Next rule or condition. Rule 3. Okay. If covalent bonds are same. If covalent bonds are same. For example, you have two resonating structures. In two resonating structures, covalent bonds are same. Okay, just a second. If two resonating structures are having same number of covalent bonds, then how to predict the stability? See, if CB stands for covalent bonds. If covalent bonds are same, then resonating structure with negative charge on more electronegative atom. Negative charge on more electronegative atom is more stable. If number of covalent bonds are same, then how to predict the stability? Then check in which resonating structure negative charge is present on the more electronegative atom. Let us see one example. This is one resonating structure. This is another resonating structure. First tell me covalent bonds. Count covalent bonds here. How many covalent bonds are present? 3 hydrogens, 3, 4, 5, 6. Covalent bonds are 6. Here 3 hydrogens, 3 covalent bonds, 4, 5, 6. Okay. Which is stable. Here negative charge is present on less electronegative atom. Carbon is the less electronegative. But check this. Negative charge is present on more electronegative atom. So this is stable. See, if covalent bonds are same, then resonating structure with negative charge on more electronegative atom is more stable. So this is more stable. Why? Because oxygen is more electronegative and having negative charge. Clear? Right. This is about rule 3. Okay. Next. Rule 4. Resonating structure in which like charges are present, adjacent with each other is unstable. Like charges means positive, unstable. in any resonating structure, if positive charges are present side by side or negative charges are present side by side, then that resonating structure is unstable. Let us see the example. I am giving two resonating structures to you. This is one resonating structure, okay. This is another resonating structure. Let us see which is stable resonating structure. See, if we go for the rule 1, rule 2, what is rule 1? Resonating structure should differ in the arrangement of electrons only, but not in the arrangement of atoms. Here atoms position means in this structure atoms position and in this structure atoms position is same. So first rule is same. So based on the first rule you cannot predict the stability. What about second one? Resonating structure with more number of covalent bonds is more stable. See, this is having how many covalent bonds? Count 3, 4, 5, 6, 7, 8, 9. Here also 9 are present. 3, 4, 5, 6, 7, 8, 9. So based on that also we cannot predict. What is the next one? If number of covalent bonds is same, then resonating structure with negative charge on more electronegative atom is more stable. Here negative charge is not present on more electronegative in this structure and in this structure also, then how can we predict? Now we will come to this rule, okay, fourth rule. What is that fourth rule? Like charges should not present adjacent positions, in adjacent position. See this. Where like charges are present, see this. Oxygen is having lone pairs, right? Oxygen is having lone pairs. Lone pair of electrons. Electron means which charge is present? Negative charge. Negative repulsion, negative repulsion. Clear? Oxygen is having lone pair of electrons, and electron means negatively charged. Electrons are negatively charged particles. This is negative, here also negative repulsions. So this is unstable. Sorry. Unstable. See. Negative, positive, stable, opposite charges, negative, positive. Clear? Right. This is about the conditions to draw resonating structures, right? Okay. Next. Plus some groups. Plus some groups. Like plus I, we have plus some groups, right? Plus some groups are electron donating groups. Electron donating groups. Electron donating groups are called as plus sum groups. Okay, I'll give you some plus sum groups. You have to remember that plus sum groups. O minus is a plus sum group. Oxygen with negative charge is a plus sum group. O minus, OH, OR, NH2, NR2. Okay. Ester, amide, ester amide. Okay, these are important plus sum groups. Coming to minus sum groups. Better to give here only, na? Just a second. Minus sum groups. What is the definition of minus sum group? Electron withdrawing groups. See, what is the difference between minus I, minus sum, plus I? I'll tell you. Electron withdrawing groups. Electron withdrawing groups. Important minus sum groups. NO2, cyanide, aldehyde, ketone, carboxylic acid. See one important point. Here also I am writing ester. I wrote ester here. Here also I am writing the ester. Look at this. But you only tell me what is the difference between these two. This is ester. This is also ester only. And similarly, amide, I am writing amide again. Means ester and amide comes under two categories, Y. See, why ester and amide are considered as both plus M and minus M groups. Look at this example. This is benzene, right? Benzene, right? I am writing ester on the benzene. You tell me through which atom ester is connected. This is benzene, no? This is benzene, no? Benzene. This is ester group. Ester group is connected to benzene. Ester is connected to benzene through which atom? Oxygen atom. Oxygen atom. So when ester is connected to benzene ring or any other unsaturation, okay, through oxygen, then it acts as a plus M. That's why look at this. I wrote oxygen here. Here we can write benzene or any other unsaturation. Okay. Similarly, if amide is connected to benzene ring through nitrogen, here N, then it acts as a plus M. Clear? Now, when it acts as a minus M group, look at this. I am taking benzene here. I am writing ester here. You tell me. This is ester and this is benzene. Both are connected by which atom? Carbonyl carbon, not with oxygen. Through oxygen, right? Clear? So here ester act as a minus M group. So remember, which of the following groups can act as both plus M and minus M groups? Esters are having ability, and amides also having ability to act as both plus M and minus M group based on the attachment. You tell me, what is the effect caused by ester in this structure? Plus M or minus M? Tell me. Plus M. See the attachment. What is the effect caused by ester in this structure? Minus M effect. Very important. Clear? Right. And I told to explain what is the difference between minus M and minus I, plus M and plus I. See, plus I means electron donating only. Plus M also electron donating only. Plus I means electron donation through inductive effect. Okay. Electron donation means tendency to donate, not donation completely, tendency to donate. In inductive effect, plus I effect, electron just try to move towards unsaturation center or electron diffusion, try to move, but they won't move. But in plus M effect, in resonance effect, electrons will move completely. For example, one friend came to me, he asked one help. I said that I will help, but I didn't help him, that just I will help. I said I will help. Okay. I didn't help. That is the thing. Inductive means just a tendency to give only. Okay. Not complete shifting, not complete transfer. But in plus M effect, in plus I tendency, in plus M completely electrons will transfer. That is the difference. Clear? Right. Okay. We completed plus M groups and minus M groups. Okay. Right. Let us see how to draw the resonating structures. This is also very important. We completed conditions to draw resonating structures. Let us see how to draw resonating structures. Just a second. Right. Drawing resonating structures. Drawing resonating structures. We know what are plus M groups and what are minus M groups, right? Again, I am writing some plus M groups, some important plus M groups. OH is plus M, NH2 is plus M, okay? NHR, NR2. I given some plus M groups, right? Let us see the order of plus M. In inductive effect, I given the order, right? Minus I groups order and plus I groups order. Here also, but I'll give you only few groups order only, and that only important. Let us see. Nitrogen NH2 is a strong plus M group. NH2. Next NHR, or simply you can just remember these only. NH2, nitrogen after OH. Okay, OH. After that, this double bond. The double bond also having some plus some effect. I didn't include that, but just you remember. CH3. CH3 is considered as a plus some group. It is a type of special category. Based on the hyperconjugation, it will act as a plus M. So remember this. NH2 is a good plus M group. After that OH. After that double bond. After that methyl group. Because I use these 4 examples during the questions, that's why I given. So whenever you get these 4 examples, which is a good plus M group, NH2. After that OH. After that alkene, and least CH3. CH3 donating power is least, less plus M group. Okay, right. What is our heading? Drawing resonating structures. Okay, right. Drawing resonating structures means, see, I said resonance means shifting of pi electrons or non-bonding electrons, etc., etc., etc. Like now, let us see how to shift the electrons from one place to another place, and after shifting, which atom will get positive charge, which atom will get negative charge. Okay, this is also very important to do the questions based on the mechanism, right? Let us see carefully. Very easy. Okay. I am drawing resonating structure for this. This is another resonating structure. Look at this. This pi bond is there. Imagine this pen as a pi bond. Shift this bond. Correct. Here one bond is. I'll use another color, different color. This pink color bond is there, na? Pink color bond. I am shifting that bond in between these two. Right? Look at this. This pink color bond is shifted in between these two. Right? This carbon atom is losing the bond, right? See. This carbon is losing the bond, so it will get a positive charge. And this carbon atom is gaining the bond. See, this bond is coming towards this carbon. Bond means negative only, na? And here it is positive. That's why neutralization is taking place. Neutralization is taking place. So if I ask you to draw the resonating structure for this, you have to draw this. Okay, right. Let us see another example.